Hey, everybody, and welcome back to the Blind Spot. So today it's just Marcelo and I. Evan had some family stuff that he had to deal with. So today, actually, the topic is really going to be kind of about string theory and the idea of theories of everything from our point of view. Like Marcelo and I we've written stuff together and separately about, we're known as critics of that sort of domain. But we also want to give you a little bit of our history as graduate students and young professors about how and why over time we came to this. So that's kind of the plan for today. I'll also note for our listeners, I know that all of our listeners are really big Met fans of the New York Mets, and I want to let everyone know that, okay, we dropped down to second place, but don't lose heart. I know all of our Brazilian listeners are really interested in the New York Metropolitan baseball team. So just letting you guys know things are going okay here. Okay, and with that, I'll also note that one of our listeners on Blue Sky asked that we try and give some background on some of the science. Like sometimes the science terms were coming too fast. So we will make an effort to do that today. So Marcelo, let me start by, asking you about your own path through this, because unlike me, you worked directly in this field. And so just a little bit like as a graduate student, this whole idea of theories of everything, sort of your own experience with them, across at least the early parts of your career.
Sure. So, no, that's a lot of fun. And by the way, you talked about the Mets, and I just found out that the Brazilian national soccer team's coach is Italian. So I don't know what the heck is going on. Like the world is really going crazy. It must be old news for all the people, but I was so shocked when I heard that. I mean, come on, right?
Really?
Yeah, it's just insane. Yeah, so I was a dreamy kind of guy, and I was very much in love with the whole mystique of actually I have to say, the great white man that are predecessors of science, in England and in Germany. And when I got into physics, and I have to say, I started doing engineering. My father would not let me do physics.
I didn't know that.
He's like, are you crazy? Who's going to pay you to count stars? I'm like, but Dad, physicists don't count stars. Doesn't matter. Brazil needs engineers. You're crazy, and you were talking about the late 70s in Brazil, right? And it's true. Brazil was growing economically, and they had a nuclear program starting for power stations only. And so I relented, and I'm like, fine. So I did go into chemical engineering. And after the first semester, it was very clear to me that was not a good idea, because I was doing really badly in analytical chemistry and stuff like that, and really well in calculus and physics, which fortunately, in the Brazilian curriculum, it's kind of similar in the US, actually. You take a lot of overlapping courses that you can use from engineering and physics. So the first couple of years are kind of like the basics, and you can do that. Anyway, so I got into physics, and I was very dreamy. I had this autographed photo of Einstein, right? That was my bar mitzvah present, being Jewish when I was 13. Do you even know this? I don't think I even told you this story.
No, I've never heard this story before. That's awesome.
Oh my goodness. So Einstein went to Brazil in 1925 and to raise money for the Zionist cause. And it wasn't just Brazil, he went to Argentina as well, because you're talking being Jewish in Europe in the mid 1920s and then later on. And so he really was trying to canvass for a state for the Jewish people. Anyways, so he goes down there, and he has to give this speech at the banquet at the Club of Engineers in Rio at 1925. It's kind of way back there. And his two hosts, one was my maternal grandfather, and the other one was my stepmom's uncle.
Wow.
And so this stepmom's uncle was called Isidore, and he became really Einstein's guy in Rio, and took him around and all that. And it turns out that the night of the banquet, Einstein was not wearing a tie. And he says, you can't go to the banquet without wearing a tie. So he said, okay, Albert, I guess he called him Albert, not Birdie.
Yeah, listen, you need a tie. You can't show up at the place without a tie.
So he lent him his tie. And then Einstein said, okay, the least that I can do is let's take a picture together and I'll autograph it and I'll be wearing your tie on the picture. I'm like, and Isidore did that. So that tie remained in the family. And because I was a bit of a more nature than physics nerd when I was an early teenager, I got this as a present, right? Which I still have with me.
Amazing present, though. I mean, like, wow, a signed autograph of a picture of Albert Einstein with your grandfather, right? Or your great, somehow related to your family.
Step grand uncle, I guess he was Isidore. My other grandfather didn't appear.
Is it somewhere in your? Or is it?
Yeah, I have it with me here in my house. Yeah. And I made copies of it. But anyways, the point is that from that time on, I started to read his books, especially The Evolution of Physics. I don't know if you read that book. He's a popularizer of science too, you know?
Yeah.
That is awesome. When people say, oh, people shouldn't be doing that. I'm like, excuse me, Galileo did it. Right. Einstein did it.
Right.
And so Feynman did it. I think we're in good company. We can do it too, you know? So go and talk about science, the public. But anyways, long story short, I was completely in love with the idea of, let's say, unveiling the mysterious code of nature through geometry. Right? Which is what Einstein did, right? I mean, that was his thing.
Right. General relativity. That was what he was doing.
Right. Yeah. I mean, the special theory of relativity was the Pythagorean theorem. Really, that's all the math you need for the special theory. And then when you go to general theory, it was about non-Euclidean, meaning geometry in curved spaces as opposed to on the tabletop, which is what we tend to.
So let's just, because of that, our viewer, let's just step back. So special relativity was the first theory that Einstein developed in 1905 that, was revolutionary. And it was all about motion and forces, but it did not include gravity. And then it took him 12 years later to develop the general theory of relativity, which then included gravity, in which gravity became the geometry of space and time merged into a single entity space-time. So that's our background.
Right. So just one qualifying point. So special theory of relativity was really about motions at constant speeds, right? That's why it's special. And in that case, it was all inertial motion. And that always bothered Einstein. I said, look, we're always accelerating, because of the action of this or that force. So we have to have a more powerful theory. And that's where his 10-year-long battle it wasn't like immediate. People have this notion that geniuses have these insights and it's all very easy for them. He struggled with this one big time, both with the physics, right? Because it was so strange, and with the mathematics, which he didn't have.
Yeah, which is right. Everybody thinks of Einstein as this incredible, super mathematician, and actually he needed other people to help him with the Riemannian mathematics, which was still pretty new then. A mathematics of spaces that were themselves curved.
Yeah. And we mentioned a little bit of that in the previous episode when we talked about, the closed spaces and open spaces and flat spaces. But since you mentioned this thing about Einstein and his mathematical limitations, there's this story about him when he was much, much older, like in his early 70s, so almost dying. He was actually teaching math to a young girl right next door, his neighbor or something like that. And the story goes that one day she says, I really have serious problems with mathematics. I can't get this, and Einstein said, I can assure you that my problems with mathematics are much bigger than yours.
That's right.
So he knew, he was just a profoundly intuitive thinker, and math was really a tool that, and I could relate to that, I don't know about you, but I had to struggle to learn the mathematics I needed to become a theoretical field theorist. Field theories are the theories that describe classical general relativity and electromagnetism, and then all the quantum theories that describe, the nuclear forces. And
yeah, it's interesting because, I think you are a much better theoretical mathematical physicist than I am, but I have the same thing, that it was not trivial for me. I loved it. I fell in love with it. The beauty of the math. I was, always, as you said, dreamy. Like when I first started encountering mathematical entities, I was just swept away by them. But, I've always considered myself, like when it comes to mathematics, I'm a woodworker. I'm a good, I'm a cabinet builder. Like nobody's going to come to me to build like, a beautiful sculpture. But if you want some cabinets, a theory, that work and are going to hold up for a while and the hinges won't fall off, I can do that, So it's like I always felt like I knew enough math, first of all, to be in love with it and to understand sort of what it's about, and to be, somewhat useful with it. But like, the people, and I've met people who are just drive through it. They just see through it immediately.
Right.
It's
not easy.
Yeah, I mean, it's like that.
Right, in high school, you have the geniuses that got everything so quickly. I'm like, God damn, how'd they do that? But then, anyway, something clicked during the university years, right? And the more I found out about Einstein, and then we mentioned also Steven Weinberg, right, in another episode about his book, The First 3 Minutes, and the unification of the electromagnetic and the weak forces. And I said, this is just beautiful, because what these guys are trying to do is to geometrize all of nature, to create truly a mathematical code that could explain the fundamental nature of reality. I mean, I'm using these words because when I was in my early 20s, this was like, whoa, man, this is, how could you not do that?
Right. You got chills out of it when you thought about the possibility that I am literally reading the language in which the fabric of reality is written. It was a quasi-religious, romantic ideal.
Exactly. I think you nailed it. It was quasi-religious and definitely romantic. The idea of the romantic thinker on the top of the mountain figuring things out, right, on a piece of paper. Because these guys just use paper and pencil, right, which is kind of amazing. So when I got to England to do my PhD, it turns out that by that time, so I'm talking about 1982, supersymmetry had been invented in the mid-70s, and it was all the rage in particle physics. Everybody was like, yeah, supersymmetry, and what the heck is supersymmetry? We need to explain, because it's so important for string theory, because it's not, string theory is super string theory, as you mentioned before. And so where is the super coming from? And so, people, basically theoretical physicists and high energy physicists and classical general relativity physicists, they're always looking for symmetries. Symmetries are ultra important, right? Because they simplify the mathematics. They reveal a sort of underlying order and beauty, below the surface of the complicated and chaotic and ugly appearances, And so this is like, wow, maybe you look at the world and it looks complicated, but if you dig deep enough, you will find the beauty of mathematics, true symmetries, which are translated into the way particles interact and gravity interacts. And that is wonderful, right? I mean, that was the beautiful thing.
Right, but let's just talk for a minute about, okay, what do we mean by a symmetry, right? So a circle, a circle, I can rotate a circle anyway, and it looks like a circle. I can take a triangle, and if I rotate it by, there's 3 different, angles I can rotate it through where it looks the same, right? So these symmetries are the ideas that you can change something, but the underlying equations or the underlying appearance or the underlying effects don't change. And that is what we mean by symmetries. And so physicists have gone from that very sort of geometric symmetry of just like, yeah, a circle, no matter how I look at a circle, it looks like a circle, to these like very abstract levels of order that also reveal abstract symmetries, which have proven powerful.
Right. And so this connection between symmetries and conservation laws, right? I mean, that's the other, right, which are essential in physics, right? So we want conservation laws because they are sort of like the secrets of the universe. So when people say energy is conserved, right, or momentum is conserved, you go, wow, what does that mean? It means that in every interaction that you see in the physical world, like 2 particles colliding or the Earth going around the sun, energy is being conserved and momentum is being conserved, and angular momentum. And so the question is you can relate those conservation laws, right? So energy before and energy after, momentum before and momentum after, and in between is the interaction, to mathematical symmetries, right? In the case of energy momentum, it's really about space-time symmetries, meaning you can move things around space and time, and you can have those conservation laws, right? Actually, it's called Nether's theorem for.
Yeah, we should just make note of M.E. Noether, a woman mathematician back in the day, right? I mean, Einstein, right? It was the turn of the century, turn of the 20th century. And it's what's called Noether's theorem, that every physics conservation law is related to a symmetry, either movement in, translation, moving back and forth in space, or rotation, or that every conservation law is associated with some kind of symmetry. Unbelievably beautiful, powerful idea.
So then the dream then with this supersymmetry story was, well, there are two kinds of particles in nature, essentially. There are particles called bosons and particles called fermions. And what's the difference between them? Well, the fermions are the particles of stuff, like a proton is a fermion, a neutron is a fermion, an electron is a fermion, and they, for those of you who know about spin, which is kind of like this intrinsic rotation that quantum systems may have, including particles, fermions have a spin, a half, a fractional spin, right? It means an electron can rotate around itself this way or the opposite way, and there are only these two options. And so you have this one half, spin a half, right? So particles that make up stuff are fermions. And the Fermi here comes from Fermi, the guy, Enrico Fermi, right? Who was another spectacular thinker. And then you have the bosons, there's nothing to do with boson. It has to do with Bose, which is the Indian guy, which happens to be in the same family as the speakers, right? The Bose speakers, that's where it's coming from. It's like, anyways, and those are the particles that are responsible for the interactions between the particles of stuff. So, for example, whenever electrons interact, they exchange, and I'm not going to explain this to you guys right now, but they exchange photons, which are the particles of light. And this exchange particles, and photons are bosons, right? And they have an integer spin 1, right? And you go on with that. And so you have these two particles. They're very different because particles of stuff don't like to be squeezed together very much, right? There's something called the Pauli exclusion principle. So you cannot, and that's why you may have heard people of, white dwarfs and neutron stars who are stabilized because gravity's trying to squeeze these balls of electrons in the case of white dwarfs and neutrons in the case of neutron stars. And they don't like that. Said, no, don't squeeze me into a singularity. They squeeze out. And that's essentially what fermions do. Bosons are the opposite. They're like, yeah, united we win. Let's do it. Let's be together. Anyways, and so supersymmetry is a symmetry that says that to each particle, which is a boson, there is a supersymmetric partner, another particle, a new particle, which is a fermion. And so you can rotate, just like we talk about rotations, a boson into a Fermi.
In this abstract space, right? This highly abstract space of different particle types, you can rotate, a boson into a fermion, right? And that was the idea.
That was the idea. And it's a very cool idea because it's beautiful, first of all, because then you have this profound unification between the stuff that exists in the universe, both the stuff that makes up us, like, and the particles that make the interactions. And that was mid-70s, 74 or so, right? And so superstrings use supersymmetry as a fundamental part of their, let's say, their mathematics, right? So they respect supersymmetry. So, and in the mid-80s...
Let me just ask, just to sort of, move up, because we do want to get to with the introduction, sort of string theory appearing in the physics, and particularly in our lives as graduate students in the late 80s and early 90s. So when does superstring theory begin to appear, certainly as for you as a graduate student, as a possibility. You're doing a PhD in fundamental physics, what we call high energy physics. I want to talk about the culture of high energy physics in a little bit, but when does that appear for you?
Right. So actually, string theory appeared in the 70s to describe an attempt to describe why. So protons and neutrons are not elementary particles. That means they can be broken down into smaller stuff. What smaller stuff? Smaller particles called quarks, right? So really quarks are the ones that are the fundamental, as far as we know right now, constituents of these particles that we know as protons and neutrons that make up the atoms. But the big question is, why are the quarks always stuck inside the protons? How come they can't get out, right? And there's this thing called confinement. So they are sort of stuck in there. And one of the ideas to explain that is that they're connected by strings. So you can't really stretch. Every time, it's just like a rubber band, right? A rubber band, you have these two pieces, you try to stretch it, move them away. Eventually, the rubber band is going to snap. And what do you get? Two rubber bands, identical to the first one. So string theory actually came from quarks first, for trying to understand.
In the mid-70s, that was the first attempt to sort of,
Lenny
go beyond
Susskind,
point
actually,
particles and start thinking about one-dimensional strings as a, quote-unquote, strings as a fundamental entity.
Exactly. And Lenny Susskind, who's still going strong, as a string theorist, he was one of the guys who did that. And so was another one called Veneziano. So there were some really, really amazing theorists that were working on this. And then they suddenly realized that, wait, if you apply supersymmetry to those old string theories, maybe you can actually show that those superstrings can describe all the particles of nature. So pause. How the heck does that happen, right? Because that's really the essence of the whole story. It's a profound ontological, it's too bad Evan is not here today, it's a profound ontological shift. It's a different narrative of what is the stuff that makes everything, right? Because up to then, what particle physicists were looking for were the fundamental particles of nature, right? Just like the atoms is that which cannot be broken. So what are the fundamental building blocks that make up everything else, right? So an electron is a fundamental building block. We just learned that quarks appear to be a fundamental building block. So you make a little list, right? And those are fundamental in the sense they cannot be broken down into anything smaller. String theories say that that is not what you want to look for. You do not want to look for little point bits of mass, the particles, but the fundamental elements of physical reality are really vibrating strings. Those vibrate just like in a guitar, but sub microscopic sizes. And just like a guitar, if you ever play a guitar, you can play different sounds on it, which means the string is going to vibrate at different frequencies depending where you put your hand when you play the guitar, right? And so the idea with the strings from particle physics is that these strings can also vibrate at different frequencies. And if you create a theory in the right way, using supersymmetry, you actually can show, and this is beautiful, and you can't take that away, that those superstrings can only vibrate in the frequencies. Remember that frequency has to do with vibration has to do with energy. So you can associate energy and vibration, frequency, but you can also associate energy and mass because of the E equals mc squared. So there is a relationship between mass and frequency. And when you look at, okay, what are the frequencies that these superstrings can vibrate? They happen to be the particles of the standard model if you do certain tweaks here and there. So that was like, oh, and it was beautiful because those string theories, in principle, because the fundamental components of reality are not points, you don't have the singularities that you would have when you describe things as point particles. Remember how we were talking about this the other day, right? You talked about the singularity in general relativity, the Big Bang being a singularity in space-time as a point. So strings say, nope, no more points. You just have these vibrating things. And that's the fundamental shift, right? as you know, every good idea has a price.
Right.
And superstring theories, in order for them to be well-behaved mathematically, meaning not create all sorts of infinities when they interact with one another, they ask for two things. One of them is the supersymmetry, which means that all those particles of the standard model of particle physics, electrons, quarks, should have celetrons, should have quarks.
Partners, have supersymmetric partners that we hadn't seen yet, but they're out there, right? Yeah.
Photons.
So an electron has a electron, a quark has a squark. Right.
New Jersey accent, please. Squark.
Look, it's got a squawk. I made a call to a friend, asked him about squawks.
So the question, and so that was number one.
The other price was the dimensions, right? The dimensions.
Voila. Tell me about the dimensions. So what the heck was that about, Adam? You know that one because
right. So in order for these theories to work, you had to have more than 3 dimensions of space. And there were various versions, that I saw when I was a graduate student of this coming out. But I think in the end, it turned out to be 10. You needed 10 dimensions of space, 1 dimension of time. So that means there's literally more space. There's a lot more space. There's all these other dimensions. Just like in our 3-dimensional world, I can go forward or back, left or right, up and down. Now there's like a whole bunch of there's 7 more versions of that. But of course, we don't see that in our world. So what happens? So what must be happening is those other dimensions are hidden. And the way people figured out how to hide them was to curl them up, it's like taking a piece of paper, which is 2-dimensional, and rolling it up into a straw, but a really, really tight straw, so that you really didn't know. Now it's it looks like a 1-dimensional object. You've kind of gotten rid of 1 dimension. Mm-hmm. So these extra dimensions or hidden dimensions became an important part, or were an essential part of string theory. And of course, talk about like beautiful, powerful, seductive idea. Oh my God, there are other dimensions of space, and they're curled up on themselves, and so it was, even though it was, asking for something that we don't see, this beauty that you're talking about, like, wow, the frequencies kind of work out. The string theory seems to predict all the right particles, including, we must note, the graviton, right? I mean, this is, again, we have known for a while that we need to unite quantum mechanics, which is, in quantum mechanics, what we have is the standard model of particle physics, but we also need to relate it to general relativity, which at some point has to be quantized. And the particle, which doesn't appear in the standard model of particle physics, the one at least we have right now, but which we think has to exist, is the graviton. And string theory, supposedly, that pops out in string theory as well. So it was what was important about it also was it leapt from, physicists have been wanting to unite the 4 forces for a while. In the 70s, there were these grand unified theories, which were supposed to unite all the forces from the standard model of particle physics, electromagnetism, the weak force, and the strong force. That was going to be grand. But now suddenly it looked like string theory was going to do everything. It was actually going to unite, the graviton, and therefore give us perhaps a theory of quantum gravity as well. So it was a theory of everything, a TOE. So there it is in the, by the time both of us are graduate students, there's this enormous enthusiasm building for string theory that, we're going to lecture. Well, you probably were working in it. I wasn't, because I was an astrophysicist. But, we're going to lectures, and there's hearing people come talk about, there's this, seems to be just one success after another, all theoretical, not experimental. But, and it seemed really, really exciting.
It was really exciting. I mean, I was in hog heaven there, in the mid 80s in England. I mean, that was the place to be. Stephen Hawking, Penrose. I mean, Penrose was not a big string theory guy ever, right. But Hawking was, and all the guys in the University of London at Imperial College and King's College, and they all were, and the problem that I worked on during my PhD was a really fascinating problem that came from the string theory idea of having, there are 2 versions. There's 11 dimensions and there are 10 dimensions, so there is the most well, how could I put it? The best supersymmetric formulation of string theory nowadays has 9 spatial dimensions and then time for 10. And so that means that if you take that seriously, we have our 3 spatial dimensions, the ones that we move about. So you go, north and south, you go east and west, and you go up and down. So these are the 3 dimensions, right? And then you have these extra 6. And the beauty of the program was that depending on the geometry of these extra 6 dimensions, remember, you in 2 dimensions, you can have a flat sheet of paper, you can have a sphere, the surface of a ball, right? So these are different geometries, right? In 6 dimensions, you can have a crap load of geometries which are possible. And the beautiful thing, and this is why it was so awesome to work on string theory in the 80s, was that there's going to be one geometry that is going to be the one that is going to reduce to our universe. And so if we find a geometry, and it's called a compactification of these 6 extra, so they're tiny little guys. And you gave the perfect example. I have a demo here. Here's my demo for
a string for the people looking at.
If you're very, very close, it's big, right? So, but if it's very tiny, look, it's looking like a line.
Pull the string away from the camera,
and that's the idea. So it may be small at our scales, but if you're talking about very, very, very tiny scales, it may be big. But somehow those extra 6 dimensions didn't grow with the rest of the universe from the beginning. Something held it together, right? And the question is what kind of possible forces or fields of weird stuff that could make this differentiation between 3 and 6. So that's what I worked on, so it's called compactification of these extra dimensions. And why did they remain small and the others were
while
big?
Everything else was growing, while the rest of the universe is expanding. Right.
And so that was it was a fundamental question, right? Because you want the extra dimensions to stay small so you couldn't see them, right? And, I have to say, I look at that now and I can see why I did it, because it was really an awesome problem to work on. But, how do you do this? Well, you come up and you invent some fields, that will work this way and that way. And they will have some sort of, we use this thing called the Casimir effect, which Casimir effect is a beautiful thing, which is physicists always talk about nothing, right? That is there something or nothing? And it turns out that in the vacuum of physics, meaning there's nothing there, allegedly, right? As Steve Colbert would say. Allegedly, there is nothing there, but the uncertainty in the amount of energy, which is 0 plus or minus, always fluctuating,
because the Heisenberg uncertainty principle.
The Heisenberg uncertainty principle creates vacuum particles that come up and down, like bubbles bubbling in a soup, right? And those virtual particles, we call them, create an attractive force between two parallel plates, for example. And that thing is called the Casimir effect, because of this Dutch guy who actually came up with the idea, measured it to be true. So nothingness in quantum physics is actually a bubbling vacuum of particles that create attractive forces. And it turns out that if you have a spherical geometry, you can also keep the sphere small with the Casimir effect if you have the right fields in. So the calculations were horrendous, to do this stuff. I mean, it was using...
Young, I remember the calculations I was doing for my magnetohydrodynamic work of MHD instabilities in jets coming from young stars. You didn't care, pages and pages and pages. That was that was your kind of macho thing. I just did 50 pages of calculations to get one result. Yeah.
Wow, man.
We're not doing that now.
Yeah, the zeta function regularization, the zeros of the Riemann gamma function. It was just God damn. Anyway, so anyway, they gave me my PhD, and the program was beautiful because the idea was that the solution of the equations of string theory would be our universe.
Right. All right. So that, let's put a pin in that, as they say. Because, right, the equations were going to be the solution to the string theory equations. We're going to explain our universe, the one we observe.
Yes.
Because now what I want, we've got like 20 minutes left. I want to sort of describe where, from our point of view, things went awry, right?
What
and
happened?
It was both, a question of physics, and it was a question of the physics community, right? So, so from my own point of view, right? So I'm not working in this, right? I am 2 or 3 subfields adjacent, right? I'm not doing high energy physics. I'm not really doing cosmology. I'm doing astrophysics, but theoretical astrophysics. But I always had a very strong interest in, these kind of fundamental questions, both philosophically and scientifically. So, whenever, when I was a graduate student at the University of Washington, and then I did my, went to Leiden for a while, and then finally got my job at Rochester. Watching, we're bringing people in, they're coming, talking, giving these string theory talks, and it was really interesting. It was really exciting. And in fact, a really important story from my point of view is around 2002, when and also in popular culture, Brian Greene, I think in the mid 90s or late 90s, writes his book, The Elegant Universe. And so now suddenly there's this, a lot of talk in the media about like, wow, we're on the verge of a theory of everything. We at the University of Rochester we're doing a hire, we're looking for a faculty member, and we, decided we'd look for some a string theorist, right? And this is at the height of everything that's going on with string theory, all the work on what are called branes, the idea of like, well, now we have to move to these extra dimensions, and we should be thinking about, the physics in, highly in more than 3 dimensions. And we tried to hire somebody who actually had a partner who's also a string theorist, and we put out an offer, and the couple got an offer somewhere else. And I'm telling you this, and we were like very sad. But now, looking back, I think we dodged a bullet, because what happened within a year or two is there was the discovery of the string landscape, which there was the recognition that like, oh, string theory doesn't give us a solution for our universe. What it gives you is a solution for 10 to the 500 universes, right? And our universe just happens to be one of them. And we talked about this last time, and so I don't think we need to go into it too much again. But that was really the beginning where string theory went from what was going to be this beautiful, elegant, simple way, not simple, not mathematically simple, but elegant way of explaining the universe, to suddenly the bells and whistles are starting to grow in it. And the idea that it doesn't explain our universe, but it explains 10 to the 500 universes. And ours, now you've got to add what's called the anthropic principle. You've got to use the fact that you exist to, sort of figure out which one of those universes you're in, or things about that. It began to start feeling like this is getting contrived, right? It's starting to feel really like, wait a minute, this is not doing what it said it was going to do. On top of that, there was the feeling that like, we're not making progress. We're not making the progress we want. We're kind of actually just making something ever more complicated. And it was around mid-2000s or somewhere in there that the first sort of pushback on string theory came. There was the book by Peter Voigt, I think it was, Not Even Wrong. And then Lee Smolin also wrote a book that pushed back. Yeah. And I'm telling people this because what has happened over the years in the physics community, not just the community of the people who are working on it, but the broader physics community, was there really started to become a feeling like this isn't working, right? This is not, this is just not turning out. This is not what you promised us, right? So a little science fiction reference here. There's the movie Buckaroo Banzai in the Eighth Dimension, which is one of my favorite science fiction movies. And in it, the insane ruler of the Eighth Dimension, which is who's gotten stuck on Earth, keeps going to all of his workers, his drone workers, when are we going to get to the Eighth Dimension? And they're all like, real soon. When are we going to get to the Eighth Dimension? Real soon. It started to feel that way with string theory, like one talk after the other, year after year, decade after decade. And it's just getting worse. The problem's getting worse in terms of having any kind of connection to reality. So I think that's where, for me, it started to feel like, this isn't really what you guys promised us. But the problem was also that this hype machine had sort of emerged, where people were still talking about string theory like, publicly, like this is the greatest thing since sliced bread. And there became an ever wider divide between sort of, I think, what the bulk of the physics community thought about it, and then the appearance in that in the media. And I think this is a problem. I want to talk a little bit about the culture within physics, because when I was coming up, this is probably true for you, like high energy physics, studying, the fundamental nature of the particles was like the highest of the high in physics.
Yeah.
That's where like the super smartest people went to. And if you weren't, if you couldn't handle that, you did astrophysics or something else, right? There was definitely kind of a hierarchy. For good or bad reasons, it was there. And it felt like with string theory, it's like, there was this maintaining of that sort of high hierarchy, but nothing was coming out of it anymore. And so there was, in the media, there was still being this presentation of this is the ultimate science, this is the ultimate direction science can go. And yet from within science, it felt like this is becoming more artificial and it's not delivering. And I think that's where the pushback really kind of started and continued. And that's why, Marcelo and I have been publicly critical of this. And then we can go even further than that. But I just wanted to, sort of lay that out, that now, if you asked most physicists what they thought of string theory, they'd be like, meh, and yet still there's this sort of sense within like podcasts and that, oh yeah, string theory. Oh, and let me make just one last point about this. It got to the point of absurdity for me, at least, when I think it was in the mid 2014, 2015. I don't remember when this was. There was a philosopher who published a book or published a paper arguing that string theory was post empirical. That, look, we can't prove string theory, but that's okay because it's the best we have. So we don't really need data anymore. We're just going to like adopt string theory because it's the best we have. And that was really, more than anything, what broke the camel's back for me, because I still sort of felt like, even though some physicists would be like, oh, that's true, it's not true, I felt like there was, among the advocates, the community, there was this sort of feeling that we're going to hold on to this idea, whether there's data for it or not. Like, just to finish this part, it's clear that the simple versions of supersymmetry are not working empirically. Like, that's the only data we have. Right, yeah. That supersymmetry has been somewhat ruled out by the LHC, and yet are people going to give up on string theory? Not, the really dedicated community, no. And that's the thing that begins to really sort of feel like this is the lack of data is making this very much a sociological experiment and not the best of what science could be.
It's true. I mean, if you look historically, right, at the whole idea, you trace a line back to Plato and the pre-Socratic philosophers, in ancient Greece, who were trying to find the theory of everything. They all, the first philosopher was Thales, and he said everything is water. And, we can debate that, but the point is that he was saying there is one fundamental substance of reality, which is water, right? And then other people say, no, it's air, no, it's fire, no, it's something very, very abstract called the apeiron, but where everything comes from and everything returns to. But the point is that they were trying to find that simple explanation for everything. And then Plato took that on, influenced by Pythagoras, the Pythagoreans. So these guys, the pre-Socratics, including Pythagoras, we're talking 650 BCE, right? Before the Common Era. So a long time before. Plato is more like 300, and he's combining these two and saying, maybe you can atomize the fundamental nature of reality using geometry. So he talks about the Platonic solids as the fundamental atoms of reality. And the notion that truth is related to beauty. And here I'm talking about mathematical beauty, right? And there is that John Keats poem, right? Beauty is truth, truth is beauty, or something like this. And
that's all you need to know. Yeah, right.
And what Plato was saying is that the real answer to the searches that we have for the nature of reality are all in mathematics. They're all inside your head, right? And if you figure that out, then all goes through. And, look at Kepler, right? I mean, so if you jump 1,000 years, right, and even more, and you go to Kepler in the 1600s, early 1600s, he was trying to find the geometry of everything using the Platonic solids and said, this is how you do it, if you don't know it, it's in my book, The Dancing Universe. So a year before Brian published The Elegant Universe, I published a book called The Dancing Universe, which was basically a history of cosmological thought, right? But anyways, the point is, those guys, and I have to include myself in this gang, in my 20s and early 30s, we thought of ourselves as the heirs to the Platonic dream of geometrizing nature, right? That yes, the blueprint is there, it's all geometry. It just happens to be in 10 dimensions. Who cares, Even more exciting, but it's all geometry, right? And Einstein worked on unification. Let's not forget, for a long time, for like the last 2 decades of his life, he tried to unify, that is, create a single theory that encompassed gravity and electromagnetism, and he failed, And this guy, way before, in 1919, Theodor Kaluza, had a theory in 5 dimensions. Right. This is beautiful, right? Which is gravity and electromagnetism. And it works. It's beautiful how he does it, right? And it works, meaning you can write the equations and the geometry. You make a few assumptions about the 5th dimension is coiled into a small circle. The radius has to do with the charge of the electron. There's all sorts of correspondences there. But the point is, that was the mystique, right? That was the dream.
And that's that. I'm sorry.
Go ahead. No, that's it. Go ahead.
Thing, the mystique, right? And that, because I feel, string theory was the beginning, in some sense, of this era where I feel like, that branch of physics started like smoking their own stash, as I like to put it, right? Where the ever more insane, not insane, but ever more like wild, abstract ideas. Yeah, we're fine. Like, let's just go up. My theory's got more dimensions than yours. My theory's weirder than yours. Like, somehow, because of the power and potency of the abstractions that had come before, and then it's a very important part of the story, the end of data, right? I mean, that there was no, as we talked about last time, there's no data up in these energy regimes, right? So it becomes pure theory. And then we're being guided by somebody's idea of what is beautiful or what is not beautiful. That's the only thing. You don't have any data from an accelerator to say, your beautiful idea just died, right? That's the great thing about working with data. I can't tell you how many beautiful ideas I've had that have been killed by data. And that's a great thing. And so what happened is like these upper echelons, what we're seeing as the upper echelons of physics in the 1960s and 1970s, right? They became more and more divorced from reality meaning data. There was a sense like, well, we're still the upper echelons of physics, so we can go off and do whatever we want with our super abstract mathematics. And it just created a kind of, a closed culture of with a few like really smart, really super smart, like you got to give them all the smarts there are, but where they're, you're starting to have multiple generations of graduate students who didn't have any contact with data. And all that mattered was, were you working with the person who was seen in the community as being the smartest person? And I think that really led, from the outside view, really led the field astray, where there was just a couple of ideas like string theory that everybody piled into. And if you didn't pile into that, you were no hope of getting a job. And and the ideas just got weirder and weirder, and it's sort of, I think it's been detrimental to the field.
Yeah, the point being that, a physicist that says, my ideas are too beautiful to be wrong, is not doing the right physics, is not thinking philosophically about what it is that physics is, right? Physics needs data to be vindicated, and so that you can say, yeah, I can trust, but my model of this or that phenomenon, because it is consistent with the data, and so it's not like theories are not right or wrong. They just are useful descriptions for the data that we can measure, right? And when we think that a theory is beyond that it does not need data to be verified as a valid description of reality, then you're losing the fundamental tenet of empirical sciences, which is we are trying to describe the natural world. And for that, we need to rely on data. And if data is not forthcoming, which is always the issue, right? You can't kill supersymmetry, because we could always say, well, the supersymmetric particles are much heavier than we can probe with our particle accelerators, like the Large Hadron Collider in Switzerland and others. Or you cannot probe the higher dimensions because they're so small we can never get to them, and any kind of physics effects that they would cause are not measurable right now. People say, well, you can go to the early universe and maybe there'll be some kind of gravitational wave that you'll be able to detect that will tell you something about quantum gravity, because string theory, as we were talking about before, does away with the idea of the point singularity but there's this whole other way of thinking about quantum gravity, which is not coming from the particle physics tradition. It's coming from the general relativity tradition, which is quantum gravity, which is what, Lee Smolin and Carlo Rovelli and a bunch of other really smart guys are doing, which is not that, which is very different. They'd say space-time can actually be tessellated, can be broken down into little chunks. And it's a different way of thinking about the connection between quantum physics and gravity, which is still in 3+1 dimensions. And they're sort of rivals descriptions of what's going on. And right now, we really don't know where to go with that, right? People have all sorts of possible ideas. For example, some of these theories give what's called bounces at close to the beginning, meaning that there is no singularity. There is actually a finite volume, which is the bounce, and things may bounce back and start growing again, or there maybe have been bounces back in before the Big Bang. Some people get annoyed by thinking that the Big Bang is the beginning of everything. So there are all sorts of very interesting but very wild ideas out there trying to come around the issues of we don't have any data to validate this stuff.
Right. I actually, just to maybe end up, when I look at this, right? And again, it's nobody's fault. I'm not like, I think all the string theorists were honestly pursuing what they love. I think it's just it became a closed system in some sense, which was detrimental to the field. But also, if I have to look to the future, I think there's a possibility that this whole field sort of just kind of attenuates, right? Because there's how many generations can you have where there's no data and all you're doing is just speculative, somewhere between mathematics and physics, and maybe neither one of them being done really with any kind of hook to reality in them. So there's a possibility, like if we don't find a way to get data to those about those earlier or those the higher energies, true early universe times, that physics will move on. If you're 10, 15 years from now, if you're a bright young physicist, you can either go into this field that for now 60 years has had no data, endless mathematical theorizing, or you could go into quantum information theory where they're building quantum computers or something. I think the smart, bright people are going to go into the fields where there's a, as somebody once called it, a visible frontier. Like you can get right to the frontier, get some new data, and push forward. And I think, for us, I think we both agree with this. Complex systems, the physics of life, that's one domain. But certainly, like domains of condensed matter theory, quantum information, tabletop quantum experiments. There's just other fields that are there's a lot more interesting things happening because you're actually talking to nature. And my sense is that unless something happens soon, in 20 years, just not a bright young person isn't going to be sort of seduced the way we were kind of seduced, that this is the only thing. This is what truly the frontier of physics, quantum gravity is the frontier of physics. Because there's not much to do there other than, kind of sterile theorizing.
And if you want to be a real heretic, right, you can say, why do you need to quantize gravity exactly? Because if you really go, and I think we need 2 more minutes just to go into this, because it's a very important point, because the way the argument goes, right, is, well, if you believe in the Big Bang and the origin of the universe, and if you go backwards in time, like we explained before, and if you use a classical theory of gravity, like general relativity, at some point very close to the beginning, things will all blow up in pressure, density, energy, everything, because a classical theory goes to a singular point and you're dividing by zero and then boom. And then you say in the universe, the distances are so small that you have to treat everything quantum mechanically. Hence, that's one. The other one is the singularity, another singularity, actually similar, inside the black hole. You say, what's going on inside a black hole? Same thing. If the black hole is not spinning, you have a point like singularity at the very core of the black hole. And if the black hole is small and evaporates, do you have a singularity exposed? How could you have something that is a point that has infinite gravity in nature? There is something called the cosmic censorship hypothesis.
Right.
They say, no, that's X-rated. That's actually a Penrose thing. Can't have that. People say, well, what's going on? Then maybe there's quantum gravity. But the point is, the reason I'm bringing all this up is that we have no idea what happens inside a black hole, right? You can describe mathematical theorems about the point singularity, but we really don't know what goes on beyond the event horizon. And we also have no idea of the universe in its early origin. So the real arguments for quantum gravity come from two unobservable, or at least non-observed, physics realms. I remember I mentioned this to Freeman Dyson once, Freeman Dyson, for those of you who never heard of him, was one of the greatest physicists of the 20th century. I had the luck of having amazing conversations with him. And he said to me, until somebody shows me a graviton, which would be the quantum particle related to gravity, just like the photon is the quantum particle related to electromagnetism, I have no reason to believe in anything related to quantum gravity. So it's an empirical point.
So, yeah, and I think this is a nice way maybe to close up what we've done. I think the problem really comes down to data. And listen, if we find some way to get new data where these theories can be tested, really, not at the edges where, you've measured some 10 to the minus 36 deviation between one thing or another. And now,
Right.
And you're going to now write wild, theoretical papers, but we can really get in and start, really testing something in detail. I fear that these fields, not that they're not interesting, they're, but that there's just, how long can you not have data? And in the history of physics, you can't go that long without data, where people just sort of move on. And I think, that's been the problem for string theory. So, so I think that's, there's other things we could say about why Marcelo and I have, written things together and separately about our criticisms of both the string theory as the kind of culture that goes around it, but also sort of the science, the scientific, the empirical science related to it. So,
and then
go ahead, Marcelo.
Just my last thought.
Your closing thoughts on this.
My last thought is that, nowadays, even though I grew up in the Platonic perfection and beauty is truth thing, which is the theory, which is really an ontology of perfection in nature, right? You want the symmetry. And the more I look at nature, the more I see how imperfection, the other idea, imbalance, and asymmetry is really the creative force between all the dynamics that happens in the universe. If you look at it, and there's the asymmetry of time that allows us to be here, the matter and antimatter asymmetry, there is asymmetry in the structure of the molecules of life. And so maybe, we have to let go of that Platonic ideal and embrace an aesthetic of the imperfect as the real, the real core of what's happening in the natural world.
Which is a beautiful thing, because that's life. Life is a freaking mess, right? And so, in some sense, right, the Platonic ideal was a quasi-religious idea of, to just hear the angels and their perfect songs. It's an attempt to leave the world, right? That this world sucks, but there's this more perfect world behind it. And what you're saying is no, that imperfection is actually perhaps part of the fundamental structure.
Yeah. It's creative,
Yeah, and it's creative, right? That's the important part, which is the best part of actual life, is the not knowing, is the creativity, is the possibilities for innovation. So,
exactly. All right, my friend. That was so much fun.
Great conversation. I hope this was helpful for people, just for understanding where we were coming from. And there'll be more in the future. Some of the ideas, we haven't really gotten to the philosophy under this, and that when we get Evan back, who's our master philosopher, we can sort of go into some of the philosophical dilemmas that were raised by the kind of thinking that, the Platonic kind of thinking. So, all right. Well, thank you, everybody. And we'll see you in a couple weeks. Bye.
See you soon. Bye.